Welcome, everyone, to the Space Prize Speaker Series. This is episode 16. It is September 28th, 2022, and we are joined by Oliver White from the New Horizons mission and from SETI. I want to say a few words before we kick off. As usual, I'm Mark Wagner. I'm the president of the Space Prize Foundation. We're focused on empowering particularly young women to pursue STEAM education and to explore careers in the growing space industry. Those careers might include engineers and scientists like Oliver, but they may include all sorts of other folks, and that's sort of the point behind this series, which I'll dig into more. We're also joined by Dr. Leslie Anderson, who is our host and will be interviewing Oliver, and fantastically happy to have Oliver here as our guest. Now, I want to say a few words about Space Prize before we dive into Oliver's presentation and our interview. But spaceprize.org is where you will find us online. And I like to explain that the way we empower young women to pursue STEAM education and to explore careers in the growing space industry is two ways: through exciting, attention-grabbing contests with spectacular prizes like zero-G flights, where winners can experience weightlessness, and also through producing open education resources like this guest speaker series and the curriculum, which I will say a few words about. Our first contest was at the beginning of this year in New York City. We had an essay contest and a video contest across the 5 boroughs in public schools. We selected 25 finalists who got to experience a simulated mission to Mars at the Challenger Center right there in Manhattan. And they also got to experience a Yuri's Night celebration. And we sent 5 winners to Space Camp's new leadership program, LIFT, and we sent 5 winners pictured on a zero-G flight with Star Trek's Denise Crosby and our own executive director, Kim Sharia, there on the left. Really a fantastic opportunity for all of them. All of the winners from both prizes get mentors for the next year. They're connected with influential women in the space industry. And we did something very, very similar in Paris. Just last week, we announced the 6 finalists in Paris, and the winner there on the far left, Dalva, will also be taking a zero-G flight there in France. And all of the finalists also get mentors for the next year, French-speaking mentors in the French aerospace industry. So really fantastic to be a part of that. Right now, we have another Space Prize Challenge underway in Portugal. So Portuguese young women, wherever they are in the world, can sign up for that right now at spaceprize.org/Portugal. And the essays and videos are meant to be in Portuguese. So when it comes to the other side of our work, the open education resources, I want to point out you can now go to spaceprize.org/education and find our 8-part curriculum there. It doesn't just cover an introduction to space science and the history of space exploration, but it also starts with an exploration of why space matters to people here on Earth and what sorts of skill sets and mindsets kids will need to be successful in the growing space economy, whether or not they're going to space or working directly in the industry. And it goes much deeper into the new space economy, everything's happening with commercial space and various international programs. And it gets into philosophical issues like sustainability, governance, ethics, and other future implications. We're talking everything from existential threats to humanity's higher aspirations. So definitely something that I think all students should get an opportunity to experience, and it is free and available to students, educators, and enthusiasts everywhere. So that's at spaceprize.org/education. I, of course, want to mention my own book, which is something of a companion, not so much aimed at an audience of students, but certainly educators and parents and others who care, enthusiasts, if you will, but looking at how to prepare students for the growing space economy and for humanity's rapidly approaching multi-planet future. The book also looks at what school might look like on the moon and on Mars and in deep space. And it also takes a look at some of those philosophical issues as well. Now, our other open education resource is this particular speaker series. We have already featured astronauts, engineers, scientists, but also entrepreneurs, designers of various kinds, space lawyers, space historians, and many, many more coming up. So really excited to have Oliver with us today and sharing more about his deep space missions. So for those of you that are here, please do participate in the chat. Like I said, we're looking forward to your questions and participation. Feel free to use the raise hand feature. We've got a small group, so also feel free to just interrupt anytime. And you can even sometimes share screen. We've had that happen where people in the participants were sharing with us, and it just makes the episode that much richer. Feel free to use the help feature to reach out to me, or just drop me a question in the chat directly, or in the main chat, and I'll respond, hopefully be able to help you out. So any questions before we move on from here? Awesome, cool. In that case, I need to introduce Dr. Leslie Anderson. For those of you who have been watching, she has started a new position. She's now a science planner with the U.S. Antarctic program, coordinating scientific expeditions in the deep field, which is really pretty fantastic. And I understand you're going to get to do some field work, Leslie, which is hopefully going to scratch off some more spots on the map behind you. She's a former classroom science teacher. She certainly continues to work in the field of education as a consultant. She helped with development of our curriculum. And speaking of the map behind her, I always love sharing a little bit about Leslie's adventures. As I understand it, she's been to the Arctic and Antarctic. She's been involved in a number of marine biology efforts, studying turtles and sharks and neutrinos in ice core samples. So we're lucky to have her as the host of this speaker series, and I'm going to turn it over to her so that she can tell you a little bit about Oliver and kick this off.
Thank you, Mark. Good to see everybody tonight. Well, it's tonight for me. I'm in Washington, D.C., but thank you guys for joining in from wherever you are. So I'm excited to introduce you all to Dr. Oliver White, who's a research scientist at the Search for Extraterrestrial Intelligence Institute in Mountain View, California, although his residence is at the nearby NASA Ames Research Center. Since gaining his PhD in planetary science at University College London in 2010, his research has focused on a range of topics relating to the topographic characterization and geologic evolution of planetary landscapes, primarily in the outer solar system, including producing topographic maps of Io and the Saturnian mid-sized icy moons using landform evolution modeling to investigate the formation of Callisto's ice pinnacle terrain, and producing geologic maps of impact craters on Ganymede and Callisto. Oliver is a co-investigator on NASA's New Horizons mission that flew past the Pluto systems and Erupt in the Kuiper Belt in the last decade, and data returned from these flybys formed the basis of much of his current research. His main research project over the last few years has been leading an effort to produce a global geologic map of Pluto to be published by the US Geological Survey. And he has also investigated the glacial origins of the distinctive and enigmatic washboard terrain on Pluto, as well as the origins of the mounds that make up the primitive contact binary Erupt. He is the lead author of the Geology of Pluto chapter in the recently published University of Arizona Press volume, The Pluto System After New Horizons. Oliver enjoys sharing the excitement of planetary exploration and discovery with the public, and has given many presentations to high school students in the Bay Area. Very excited to welcome Dr. Oliver White, and I think you're going to start us off with a presentation that you typically give to your high school students. So we're really excited to listen, and feel free to start typing your questions into the chat, and we'll start to ask those after Oliver's finished.
Yeah, so thank you very much to Mark and Leslie for inviting me. I'm very happy to be here. Let's see if I can just move some of this stuff out of the way. Okay, that should do. So yeah, so yes, it's been quite a decade. I mean, for someone who was sort of thrilled about the idea of space as a teenager, being able to be involved in the Pluto mission has been an enormous thrill that will probably never be matched again in my career. And I was with you some of the highlights of the mission in this presentation. And yeah, I'm happy to answer any questions at the end. So just a recap of the discovery of Pluto and sort of what we knew about it up until the New Horizons mission. It was discovered in February 1930 by Clyde Tombaugh, an American astronomer, at the Lowell Observatory in Arizona. So back then it was the most distant object we knew in the solar system, but we now know that Pluto is part of what we call the Kuiper Belt, so one of these thousands of small icy objects that orbit beyond Neptune. It took, I think, only up until the early 1990s for the second object in the Kuiper Belt to be discovered. So yeah, for many decades, Pluto was the only one we knew about. We realized pretty soon after discovering that it's very small. It's only about a fifth the diameter of Earth. And interestingly, in the 80s, we discovered that it has a very thin atmosphere, which is kind of surprising for such a small object with quite a small gravity. We know that it has 5 moons. The largest is Charon, that was discovered in the 1970s, and the other 4 are much smaller, only a few tens of kilometers across. They were discovered by the Hubble Space Telescope in the last few decades. And since the Voyager missions completed, or at least finished their planetary reconnaissances in the late 80s, Pluto had a reputation kind of as the astronomer's planet. We only had sort of just we only sort of just saw it as it and Charon as a couple of dots from Earth, so we really had no idea what any Kuiper Belt object looked like up close. But eventually the New Horizons mission was funded, and it was the first to visit a planetary system in the Kuiper Belt. This is a picture of it in the Kennedy Space Center before launch. It's about the size of a small grand piano, and it was launched in 2006, and it was only a few months later that the International Astronomical Union in Paris decided to demote it as a planet, from a planet to a dwarf planet. But scientifically, we weren't especially deterred, and yeah, we knew that it would tell us many interesting things about the solar system. So 85 years after it was discovered, we flew by Pluto in the early morning Pacific time on July the 14th of 2015. That time it was almost 5 billion kilometers back to Earth, which means it takes about 4.5 hours to transmit a message back to Earth at light speed, so 9 hours if you want a return. And at that distance, Pluto is incredibly dim. It only has gets less than 0.1% of the light that we get on Earth, and so Pluto is unimaginably cold as a result, minus 380 degrees Fahrenheit. Another interesting thing about Pluto is its axial tilt of 119 degrees. Earth's is 23 degrees by comparison. So sort of like the planet Uranus, Pluto rotates on its side, and you can see that in this simulation of the flyby of Pluto by New Horizons at the bottom right. You can see that as we approach Pluto, we're sort of approaching over the North Pole, and then because it's a flyby, we only saw one side of Pluto up close. The other side was sort of we only saw at low resolution. And also because of its enormous axial tilt, the southern hemisphere of Pluto, much of the southern hemisphere, was shrouded in darkness, so we only really got to see the most of the northern hemisphere. So the next slides, I'm sort of going to cherry pick some of the best of Pluto, and as well as its moon Charon. I have these little maps here that sort of highlight in red where on Pluto I'm talking about. And the landform on Pluto that really stuck out to us, sort of weeks even before closest approach, is the big heart-shaped, bright heart-shaped feature on its surface, which is called Tombaugh Regio in honor of Clyde Tombaugh, who discovered it. And upon sort of getting the high-resolution images back, we found that the western portion of this heart, which we've called Sputnik Planitia, forms this enormous expanse of bright plains. You can see in this image here, about half the area of Alaska. And we found that on a scale of hundreds of kilometers, these plains are incredibly flat. They sort of only have relief of maybe tens of meters, maybe a few hundred meters at most. We also noticed, this is very unusual for sort of a planetary surface in the solar system besides Earth, is that there are absolutely no impact craters on Sputnik Planitia. Impact craters, of course, form when you have a space object crashes into a planetary surface and you get a hole. From the most famous examples on Earth being meteor crater. And the more craters that you see on a surface, the general rule is that the older the surface is, because no other process has acted to resurface that surface since the craters formed. So that suggests that Sputnik Planitia, as well as being very large, it's also very new. And another thing we noticed about Sputnik Planitia is that it's from spectroscopy results we got, its composition is dominated by nitrogen ice. The conditions at Pluto are so cold, so extremely cold, that nitrogen, which we're breathing right now, is actually stable as a solid on the surface of Pluto. And Sputnik Planitia is where most of Pluto's nitrogen ice is, we think, contained in enormous impact basin. And we know that nitrogen ice has a very low viscosity at Pluto surface conditions, so it's very sort of runny. So to try and explain sort of what's going on with Sputnik Planitia, we take a closer look in this high resolution image of its surface, and we can see that its surface is divided up into these these ovoid cells. They're each sort of separated by sort of these troughs that are a few kilometers across, with these central ridges running down them. And so we realized that what's going on here is that the nitrogen ice in Sputnik Planitia is actually convecting. So relatively warm nitrogen ice is welling up at the centers of these cells, then moving out to the edges of them, and then descending with the sort of pressure from each side, the lateral movement of the ice sort of pushing up these ridges at the centers of the troughs. Now, Pluto is a very cold environment, as you can probably appreciate by now, but nitrogen ice can be quite easily mobilized, even with just quite a small heat flow that trickles out of Pluto's interior, probably only several milliwatts per meter squared, compared to Earth's average mean heat flow, which is 87 milliwatts per meters squared. So you really don't need that when you're out at this very distant part of the solar system. You have all these exotic ices that are stable on planetary surfaces. You can basically do a lot more with a lot less energy than you need in the inner part of the solar system, and such is the case with nitrogen ice. You don't really need much heat coming out of Pluto at all to create this geologic activity of this convective overturn of this nitrogen ice sea. And we estimate that the surface horizontal velocities of the nitrogen ice here is only a few centimeters a year, which implies that Sputnik Planitia can completely renew itself in only 500,000 years, which is a drop in the ocean in terms of geologic time. And that's why we see no impact craters, and any impact crater forms, it'll be immediately eliminated, both by the convection and also by the sort of just relaxing away because of the sort of low viscosity of the nitrogen ice. So if we go to the southern part of Sputnik Planitia, we see we don't actually get the convective terrain, the cellular plains anymore. We think that the nitrogen ice here is too shallow to support convection, but instead we see these enormous clusters of these elongate and aligned pits that tend to reach about 1 kilometer across, although the largest can reach several kilometers across, like down here. So in addition to undergoing convection, nitrogen ice is also very susceptible to sublimation on the surface of Pluto. That is, it goes straight from a solid to a gas and skipping out the liquid phase. And that's what we think these pits are, created by this nitrogen ice sublimating and sort of putting nitrogen gas into Pluto's atmosphere. And these sort of odd sort of thumbprint-like patterns you can see, we think are due to the nitrogen ice. It's still, while it's not convecting, we still think it is actually flowing across the surface, and that it's actually sort of stress fields in the ice due to this flow is causing these pits to be sort of stretched out and elongated to form these kind of funky patterns, you see. So in addition to the plains of Sputnik Planitia, they also have one of the most dramatic landform types we see on Pluto, which are these enormous mountains of chaos, we sometimes call them, that collect together in these mountain ranges that align along the western edge of Sputnik Planitia. You can see them well in this picture here, which is one of my favorite pictures we took of Pluto. It's taken at a very low angle across the surface. You can see Sputnik Planitia on the right here, and these are a bunch of the mountains here rising up in their ranges, and you can also see haze layers in Pluto's atmosphere above the horizon here. So yeah, very cool photo. But these mountains, you can sort of appreciate their sort of jumbled, disorganized nature in this picture on the right. These can rise up to 5 kilometers above the surrounding plains. For comparison, that's how high Kilimanjaro rises above the plains of the Serengeti in Kenya. And they also have very steep slopes, up to 30 degrees. So this stuff can't be made out of nitrogen ice. It's so runny that it wouldn't be able to support this steep topography. But from spectroscopy, we do know that these are made of water ice, and water ice is kind of the equivalent of rock on Earth. It's basically the stuff that forms Pluto's crust, and at Pluto conditions, it's incredibly hard, much harder than on Earth. It's kind of like pretty much as hard as granite. So what we think these mountains are is that they're basically broken up fragments of Pluto's water ice crust. The western part of Pluto's, the side of Pluto we saw up close, is quite heavily tectonized and fractured, and a bunch of these fractures intersect Sputnik Planitia here. So we think that Pluto's water ice crust has sort of been broken up here and then invaded by the runny nitrogen ice of Sputnik Planitia, and then it's basically these blocks have fallen into Sputnik Planitia and sort of form these giant log jams with these blocks kind of grounded on the surface, on the floor of Sputnik Planitia. And an interesting thing about water ice is that it's actually slightly less dense than nitrogen ice is. The contrast is kind of the same for liquid water and solid water. Water ice on Earth. So some of these little blocks of water ice here may actually be legitimately floating in the denser nitrogen ice and being pushed around by the convective currents there. So yes, all in all, Sputnik Planitia is and its mountains perhaps the biggest surprise on Pluto. We weren't quite sure what we would see on Pluto, but an enormous nitrogen ice sea filling an impact basin with these giant water ice mountains within it is pretty much wins the prize for the least expected geological phenomenon on Pluto. But the surprises continued when we get to the eastern part of Tomball Regio, which is we're getting now into the uplands of Pluto. This is also very bright, this terrain, but you can see here it's much more rugged and craggy here. But we still also think that the reason it's bright is because of nitrogen ice here that is sublimated from Sputnik Planitia and redeposited on the uplands terrain here. And nitrogen ice being runny, it sort of runs downhill and sort of fills these little depressions and basins in East Tomball Regio here. And amazingly, we see at the edge of Sputnik Planitia, we can actually see this nitrogen ice flowing via valley glaciers back into Sputnik Planitia. You can see here these lineations in these valleys that connect East Tomball Regio with Sputnik Planitia. And we noticed that these are quite similar to what we call moraine trails on glaciers on Earth. They're shown very well in this picture of a valley glacier in Greenland here. Moraine trails are where you have debris from the surrounding mountains fall onto the glacier, then form these trails as they're carried along by the glacier to wherever it terminates. And we think the same thing is going on here on Pluto. It's just instead of water ice cutting through rock, instead it's nitrogen ice that's cutting through water ice, with water ice blocks falling and creating these dark trails on the glaciers here. So I guess the way I like to think of it is almost when you get out to Pluto conditions, you can sort of have these cosmic games of rock, paper, scissors, where you have similar landforms as you do on Earth, but the materials are involved are very different. So we sort of have like a water cycle on Pluto, comparable to on Earth, but with nitrogen taking the place of water. So yeah, Pluto kind of really opened our eyes to the possibilities of sort of the geology you can have in these very extreme environments. And if we move further east from Tomball Regio, we encounter what looks to be sort of one of the most alien and almost malevolent landscapes on Pluto, particularly helped by the fact that it was imaged at a low sun angle, so it casts long shadows. This is what we call the bladed terrain of Tartarus Dorsa, which consists of these these distinct sort of large swells. Each of these sort of swells, I'm indicating with the mouse here, are sort of a positive topographic relief, these sort of large sort of bumps on the surface. And you can see that they have this distinctive texture of this sort of rippled texture of these narrow aligned surface ridges. Now, we found from spectroscopy that another material that occurs in abundance on Pluto, besides nitrogen and water, is methane. This terrain is full of it. Methane, it's also quite volatile, like nitrogen on Pluto, but it's not as viscous as nitrogen. So when it can sublimate and redeposit, it does have enough strength to support high topographic relief. And how we think that this bladed terrain formed, which incidentally occurs across much of the equator on Pluto, is that back earlier in Pluto's history, a lot of it Pluto's methane condensed, deposited at the equatorial regions of Pluto, which has kind of a mild, sort of relatively cold climate compared to the more extreme seasons encountered in the towards the poles. And it formed these enormous kilometers thick deposits of methane, but at some point, some sort of climate change occurred on Pluto and sort of preferred sublimation of methane. And it's that sublimation that sort of formed this sort of what we call a decrescence texture, these sort of sharp ridges and broad valleys that characterize the bladed terrain. And we noticed that it's kind of similar to high altitude snowpacks you get on in water ice on Earth, generally at the equator, that form these things called penitentes and sun cups that are these quite jagged textures. Similarly, you have like sort of sharp ridges separated by these sort of bowl-shaped depressions. Again, it's kind of like with the sort of the valley glaciers, it's another instance of sort of similar landforms forming on Pluto as on Earth, but with very different materials involved, in this case methane in place of water ice, and also very different scales, since these ridges are sort of separated by kilometers as opposed to centimeters, which is what we encounter on Earth. So now moving to the south of Sputnik Planitia, we encounter sort of a truly unique landform on Pluto that will probably always remain enigmatic to some degree until we send a mission back there. But this is Wright Mons, which is a sort of standalone mountain about 150 kilometers across and 4 kilometers high. And uniquely, it has this enormous central depression that's about half as wide it is, and actually deeper than the mountain is high. And you can see it has this kind of hummocky texture sort of on its flanks surrounding it. So this has sort of had us scratching our heads quite a lot. Just its sort of bulk morphology, the fact that it's a big mountain with a hole in the top, has meant that we sort of kind of entertained the volcanic hypothesis for its origin, in which case it would be what we call sort of a cryovolcano. Instead of erupting silicate lava at sort of thousands of degrees as on Earth, instead it might erupt, you might get eruptions of water ice based slurry sort of moving across the surface of Pluto here. The thing that's confusing about it is that the size of this depression is enormous compared to the mountain when you compare it to the calderas of inner solar system shield volcanoes. Like this is a topography of Mauna Loa in Hawaii, which has a tiny caldera, and this is Wright Mons, where the caldera has an enormous sort of fraction of the volume of the mountain. So the processes that, if this is a cryovolcano, the exact processes that are involved are kind of perplexing at the moment. And some of us are also entertaining the idea that maybe it's not actually lava that's erupting, but sort of gaseous emissions, perhaps of a methane or something that is then redepositing around the surface here to form this sort of bobbly texture, sort of like the texture you might encounter in the freezer in your home as sort of methane is condensing out across the surface here. But as enigmatic as it is, it's certainly a young enigma, because kind of like Sputnik Planitia, it shows very few craters, only a few small ones, and we think it's maybe less than 1 billion years old, quite young in Pluto's history. So if it is cryovolcanic in origin, then it shows that cryovolcanism can be sustained even quite late in Pluto's history. The final landform on Pluto is completely different to all the rest. This is this dark material of what's currently called Cthulhu Macula, this enormous sort of Alaska-sized dark patch in Pluto's equatorial region here. And compared to, unlike all of the landforms we've seen so far, this is incredibly densely cratered by Pluto's standard. You can see all these sort of craters overlapping each other here, and it's therefore amongst the oldest terrains on Pluto, probably close to the age of Pluto itself, more than 4 billion years. You'll also see it's covered in this dark powdery stuff, this dark red powdery stuff, which is this material we call tholins. It's basically this atmospheric fallout. As you get, as methane in Pluto's atmosphere has ultraviolet light from the sun shone on it, it gradually generates these more and more complex molecules called tholins that then sort of fall out from the atmosphere and settle across the landscape here. And as they're continuously illuminated with sunlight, they gradually turn yellow, then orange, and then a very dark sort of blackish red. So the fact that they are dark black red is another indication of just how old and undisturbed this terrain is here compared to the other landforms we've seen. And this part of Pluto also is the most heavily tectonized. As I mentioned before, you have all these extensional fractures running across the surface. Extensional means that this is where the crust of Pluto has split apart. And across Pluto, the only tectonism we see is extensional in nature. And we think the reason for that is because Pluto had a subsurface ocean. I think it still has a subsurface ocean now, but which is gradually freezing. And since it's a water ocean, when it freezes, it expands. And so Pluto is essentially bursting its skin and creating these dramatic sort of canyons across its surface as you have these extensional fractures forming. So I'll just do a brief look at Pluto before we finish up with Arrokoth. Sorry, a brief overview of Charon. Charon, which is Pluto's largest moon. It's about half the diameter of Pluto. And in fact, Pluto and Charon are not so much a planet-moon system as a sort of binary planetary system. They orbit each other once every 6.4 days. And as you can see, Charon is large enough such that it's close enough in mass to Pluto such that it doesn't orbit around sort of somewhere in the center of Pluto, rather Pluto and Charon orbit around each other. The barycenter, the sort of center of mass of the system, is slightly outside Pluto. So Pluto describes a small orbit and Charon describes large orbit. And this gives you an idea of also how much real estate we're dealing with on both of these objects. Pluto is sort of most of the size of North America, and Charon is about half the size of the lower 48. And Charon is overall much more cratered than Pluto, so its surface is much older. It likely, there's no part of its surface that is younger than sort of 3 to 4 billion years. But there is a lot of evidence for interesting stuff happening in its early history. Like Pluto, Charon also displays a lot of very prominent fractures, some of which are even larger than those on Pluto, like Serenity Chasma here is tens of kilometers across and 5 kilometers deep, several times deeper than the Grand Canyon. And like Pluto, we also think Charon had a subsurface ocean, and that these fractures are caused by freezing of that. But the equatorial part of the side of Charon that we saw is occupied what we call Vulcan Planitia here, these relatively flat plains that show some interesting features, not least what we call the moated mountains. A good example here is Kubrick Mons. You can see this hill here that is surrounded by the plains, and you've got this sort of a few kilometers deep moat that is surrounding the mountain here. And we think that sort of what's gone on here is that Charon has also experienced cryovolcanism in its early history, but in the form of this water ice-based cryolavas that are erupting from under Charon's surface, perhaps let loose by the very same fracturing that caused all these enormous canyons here, spreading out across the surface. And because these lavas would be very viscous, they may be stopped short of topographic obstacles they encounter, such as these mountains here. And so we are left with these moats surrounding these mountains here. So in a way, it's maybe in fact somewhat similar to the Maria we see on Earth's moon, which have filled depressions on the moon, as you have these basalt lavas erupting early in the moon's history. But here, it's maybe the case of similar Maria forming, but with water ice-based lavas instead of basalt. Just moving out to the further into the Kuiper Belt, after New Horizons encountered Pluto, it sped out into the Kuiper Belt, which just a few statistics about it extends from about the orbit of Neptune to about 55 astronomical units from the Sun, 55 times the Earth's distance from the Sun. It's about 20 times as wide as the asteroid belt, and but still only 1/25 to 1/10 mass of the Earth. So very very sparsely populated, even though there are we think many objects there, perhaps more than 100,000, larger than 100 kilometers across, of these icy objects. And the plan was always for New Horizons to fly past one of these objects after flying by Pluto, but at the time, such an object hadn't been discovered yet. And in 2014, Hubble did a search and discovered this object called 2014 MU69, which has now been renamed Arrokoth, which is suitable as New Horizons' next flyby target. But it's important to emphasize this object is a completely different animal to Pluto. It's tiny, only 35 by 20 kilometers, and in contrast to Pluto, which is very large as Kuiper Belt objects go, it's still the largest we know of, and which also orbits in quite an elliptical orbit that takes it close into the Sun and then quite far away from the Sun. Arrokoth is on a very circular orbit, and so is in a very much more stable environment than Pluto is. And so we suspected before the flyby that it would be a much more primitive object than Pluto and more indicative of conditions of formation of planets in the early solar system, in this distant part of the solar system. And so on December the 31st, 2018, if you're in the West Coast, or January the 1st, 2019, if you were on the East Coast like we were, New Horizons completed the most distant flyby yet in planetary science history, when it flew by Arrokoth at a distance of a few thousand kilometers. And all of the sort of statistics are kind of similar for Pluto, but more extreme. We were sort of almost 2 billion kilometers further out, and even less light received than Pluto, and so even colder. But the thing that sort of stuck out immediately about Arrokoth is that it's what we call a contact binary. So it's actually two bodies that are joined together. We reckon that they initially were orbiting each other and then gravitated toward each other until they touch. And so just in one slide, sort of showing the overview of the geology of Arrokoth. This is a shape model of Arrokoth that we've assembled from all the images we got of it. And these lobes, they're incredibly flat for solar system objects of their size. We sort of sometimes call them like sort of beef patties, characterizing their shape. Yes, they sort of approaching Arrokoth, they sort of look like they may be spherical, but actually they're really quite flat. And you can also see Arrokoth has a similar axial tilt to Pluto's, which also rotates on its side and rotates once about every 16 hours. Now, the two lobes are quite different geologically. The large lobe has a distinct lumpy appearance. It seems to be composed of lots of different discrete mounds. And we think that that may actually be an extremely primitive texture, whereby it's preserved all of these planetesimals that are accreted at low speeds to form it back when it formed about 4.5 billion years ago. And since then, there hasn't really been any process that has acted to sort of erase the topographic signature of these lumps. So in that case, the large lobe may actually be the most primitive planetary object we've yet seen. The small lobe doesn't really appear to be quite as lumpy, and that may be part of the reason for that may be the existence of this 7-kilometer diameter crater on it, impact crater called Sky. That may have acted to sort of partly erase the sort of the lumpiness of it, maybe through ejecta released by it. We also see sort of where the sun angle is low, these are sub-kilometer depressions on the large lobe and also the small lobe. We're not quite, these may be due to some different pits, maybe do you have different causes. Some might be impact craters, some may be due to sublimation, some may actually be due to collapse pits, sort of on the sort of at the boundaries between these mounds. You may actually have voids within the lobe here that is causing collapse sort of along a line of weakness into the subsurface. We also see the sort of these relatively bright patches on Arakoth that we think tend to concentrate in a sort of gravity lows, basically depressions here, and we think there may be accumulations of loose or fine-grained, or maybe also compositionally distinct material that is sort of slowly crept downhill and gathered in depressions. The most notable sort of depression on Arakoth being the neck between that separates the two lobes, which is where you'd have basically the steepest slopes on Arakoth would be here, and so you might expect the most material to gather there. And Arakoth, this picture is sort of slightly misleading in that it's incredibly dark and very red, much darker than you'd see here, and sort of comparable to Cthulhu Macula on Pluto. In fact, if you were to see it in natural light, you'd have a difficulty making it out because there's so little light here, and plus combined with the fact that it's incredibly dark. So this just sort of summarizes how we think Arakoth formed. There's been a lot of scientists who've done modeling of sort of protoplanetary formation as in the simulation here, but we think that 4.5 billion years ago, there was this rotating cloud of icy bodies that collapsed under its own gravity and started to coalesce to form larger bodies. And at the same time, probably also formed a little rotating disk. And as this sort of more and more bodies coagulate, eventually this disk would turn into these only two larger bodies that remain orbiting each other. And well, these other smaller bodies were ejected from the system. And eventually these two bodies would sort of get closer and closer and closer to each other until they eventually touch. And essentially, that's what we've been left with for the last 4.5 billion years. We think there's been virtually no geological activity on Arakoth's surface since then. So yeah, it is incredible to realize that it's probably the most primitive bodies in the solar system that we've yet seen. So just to finish up, this slide I think encapsulates for me kind of the spirit of the New Horizons mission. I mean, in only a few days, we went from Pluto and Charon being just dots in the sky to these fully fledged, amazing worlds that will be sort of trying to figure out sort of what their story is for many years hence, and sort of keeps us wondering exactly what other surprises are waiting for us out in the Kuiper Belt and indeed in solar systems beyond our own. So that's all, and I'll be happy to answer any questions you have about Pluto or just yeah, my research and the SETI Institute.
Go ahead and stop sharing then, Oliver, and then
yes, yeah.
I know Leslie's got questions, and if anybody else has questions, go ahead and drop them in the chat. Oh, did we lose Leslie? Here she comes.
Okay.
We lost you for a minute, Leslie.
Apologies, I don't know what happened. My internet just went out. You okay?
It worked out, yeah. I think if anybody else has questions, we can start with that, but otherwise we can dive right into to what we prepared.
Tasha, go ahead.
I was really surprised to learn that there were subsurface oceans. I didn't know that Pluto had those. Um, are there any cycles of like expansion or contraction that kind of correlate with the orbit around Pluto or its rotation around the sun or its rotation around its axis as it kind of goes through those different levels of illumination?
So yeah, I think we think that it's pretty much a one-way route, that it's basically just freezing and there are not really any options for it melting again. So Pluto is just getting colder and colder as time goes on. There aren't really, yeah, I mean, it has some radioactive elements in its rocky core that is sort of the main power source, but as they decay, you get just less and less. There's no real tidal source of heat between it and Charon. There aren't any tidal cycles like you get for the sort of the moons orbiting sort of Saturn and Jupiter. There isn't really the same thing. So yep, it's just getting colder and freezing and expanding. But we think, I mean, yeah, pretty much all icy objects in the outer solar system, where it's Kuiper Belt objects or large Kuiper Belt objects or moons around the giant planets, probably have had subsurface oceans at some time in their past. Yeah.
Rebecca is curious about Star Wars 8, Battle of Crete, with red dirt under the snow. It looks like you showed us about Pluto, but are there different substances, salt versus atmospheric materials?
So yes, the main things that we've been able to detect spectroscopically on Pluto thus far is water ice, which again is the most common. It's sort of forming the crust of Pluto, nitrogen ice, methane. Now, in addition to those, you also get carbon monoxide, which sort of forms a solid solution with nitrogen. So, yes, we generally generalize splenic planitia as nitrogen ice, although more accurately, it's actually in a solid solution with carbon monoxide as well, which is also solid at Pluto conditions. Besides that, there are these tholins, which are sometimes sort of thought of as hydrocarbons, but I think they actually have more stuff contained within them, like nitrogen as well. So we sort of just think of them as complex molecules. They can kind of be a mixed bag, but on Pluto, you certainly wouldn't get more than the stuff that we see on Pluto, sort of carbon, hydrogen, and nitrogen would form them. No salts, really. The only other thing we've detected really is ammonia, which in fact we think occurs in a few places where we think we may be getting cryovolcanism. Ammonia doesn't really last for that long on the surface before breaking up and sort of being invisible, undetectable spectroscopically. So that may be another reason, another cause to think that we may have had quite recent cryovolcanism on Pluto's surface. But yeah, no salts like we encounter in like the Galilean satellites. Yeah.
Great question, Rebecca. And Tasha has a question, and I'm going to give Oliver a chance to answer, but also Tasha, on November 9th, we will have somebody from the James Webb Space Telescope that's going to be coming, so we should be able to ask that question again. So if James Webb Space Telescope were to observe Pluto, what new insights do you think might come from that?
Yeah, so this is quite topical because at the team meeting a few weeks ago, New Horizons team meeting, we learned that I think James Webb Telescope is going to be looking at Pluto soon. In fact, it may already have happened. We might discuss it at our next meetup. So I think the thing with James Webb Telescope is that it observes in the infrared. Well, it has a better resolving power, observes in the infrared. So resolution-wise, it may not be enormously better than what Hubble has managed, which gave us the best imaging we had of Pluto before New Horizons. But I think it may be just enough to give us an idea of sort of how Pluto's sort of brightness across Pluto's surface is changing with changing seasons, because activity on Pluto these days, as well as sort of convection in splenic planitia, you also get sort of seasonal transfer of volatiles between the winter pole and the summer pole. So yes, so that would probably be its main sort of value that it can contribute. I mean, it's on the far side of Pluto. It's certainly not going to be able to resolve anything better than New Horizons did. Even though the imaging wasn't that good from New Horizons, it's certainly far better than anything James Webb would be able to get. So yeah, I think sort of any seasonal differences, perhaps sort of at the largest possible scale, like sort of hundreds of kilometers is what it could bring to the table. But yeah, you may well find out soon enough. Yeah, exactly what it can do. Yeah.
Very exciting. Thank you for sharing that. Rebecca wants a follow-up question. What causes the pressure for the ice volcanoes to erupt?
So yes, so water ice, as I mentioned, is very inert at Pluto conditions, and there isn't really probably actual heat for it to sort of erupt. So really the main thing that could cause water ice to burst out, or rather liquid water to burst out and then sort of rapidly freeze to water ice, is overpressurization in the subsurface ocean. As the ocean is freezing, it may cause sort of excess pressure in parts that is then sort of forces the water through sort of up to the surface and maybe enough to reach the surface. It would be helped on its way with impurities in the water that sort of would lower its melting point, would allow it to sort of just stay as liquid water for longer as well, sort of like ammonia or sort of maybe even nitrogen, sort of somehow mixed in with it. Yes, certainly, yeah, the more impure water is, the lower its melting point is. So that would certainly help it on its way. But yeah, overpressurization from freezing of the ocean is kind of how we figure it would get out. Yeah.
Is it because like water freezes or water expands when it freezes?
Yes, that's right. Yeah.
Oh, gotcha.
Tasha, did you have another question that you wanted to ask?
Sure. I guess when do you think, probably maybe decades, but when do you think you'll be able to see Pluto in that same resolution or better resolution again? So you'll be able to see terrain, surface changes?
Probably not in our lifetimes. I think, yes, I think it's going to be an awful long time before another mission, whether it would be a flyby or more, it would be much more worth it to try and make it an orbiter around Pluto. But I think a lot of other places in the outer solar system are going to get more love in the time being. The latest NASA decadal survey has given the highest priority to a mission to Uranus to orbit around there. And there's also been sort of enthusiasm for a Neptune mission as well, which would be good for us solid surface planetary scientists, because Triton, its largest moon, we think is a captured Kuiper Belt object and provides a lot of interesting fruit comparison with Pluto. But yeah, Pluto itself, it's going to be an awful long time. Yeah, I think. Yeah. I mean, yes, it's maybe some of us will try and make the case for earlier for going back, but I think other places will probably be prioritized sooner. Yeah.
We're going to try and ask a couple of Laquita's questions before she has to jump off. So two-part question here. Pluto's subsurface ocean seems to freeze and melt. How has NASA determined a calculation for this water cycle given data collected from New Horizons? And the second part of the question, or second question, could the water and rock forms on Pluto indicate nutrients for life forms?
So, yeah, I don't think it's really melting so much. I think it's pretty much once water is frozen on Pluto, it's generally quite difficult to get it to melt, except in maybe small quantities if you have the sort of right conditions of pressure and sort of melting temperature lowering. Yeah, I mean, this is kind of like cutting edge science. A lot of some other researchers who focus more on the interior of planets there are certain groups that have sort of focus a lot on the interior of icy satellites, and certainly my old University College London, there's a whole group devoted to doing sort of pressure. Sort of they have pressure chambers where they can submit water ice to extreme pressure, and so they sort of form what are called like the equations of state to sort of understand how sort of both water ice and water ice mixed in with other impurities behaves at these extreme instances. So it's kind of partly a mix of theory and sort of whatever experimental data we can glean sort of in these presses that sort of give us an idea of sort of how it will behave. But some things like nitrogen and methane, I mean, this is kind of, there's hardly any research done on this up until the New Horizons. It was such an abstract concept. No one had seen giant nitrogen ice seas before, or sort of giant methane ice deposits. So there's a lot of experimental work to be done on that side of things. And hopefully, yes, labs will sort of turn their attention to that soon. As for the water, so yeah, as for the water rock forms, nutrients for life, uncertain. And I mean, it's kind of, a lot of people are thinking with this, particularly with respect to Europa, which is somewhere where has a big subsurface ocean that's probably the subsurface ocean sort of makes contact with the surface much more than it ever would at somewhere like Pluto. And even there, sort of the questions is whether just a subsurface ocean is enough. In particular, one question is sort of to what degree do you need light to sort of instigate sort of the reactions necessary to sort of generate sort of what we recognize as sort of organic systems. Because even with if you have some subsurface volcanism sort of at the ocean sort of rock boundary, and you have sort of enough sort of heat there, yes, I think light is sort of the big question as to whether you could whether you agree to with that, whether you need that to allow life forms to exist.
Thank you so much for your answers. Thank you, Laquita, for those questions. We're wrapping up towards the end of our time, but I wanted to make sure we got a chance. If there's anyone else that has a question that they'd like to ask Oliver, now is your chance. If you want to unmute, you're welcome to do that.
Well, one I would love to end on, just for the sake of this series, is Oliver, what could you say about your path here? How did you get involved in this work, or what would you say to students who might be interested in this kind of career?
So yeah, I mean, my sort of path through this work was just an initial fascination, firstly in geology, and then that sort of mixed with space to create a fascination with planets, and just sort of found it remarkable how different they all are to each other, and sort of wondering why that is. I mean, yes, and I studied at university in England sort of at a time when University College London offered a planetary science degree. Sadly, it doesn't anymore. And since then, it's sort of been fairly standard going through sort of like postdoctorate positions, which are sort of temporary research positions by which you get to focus entirely on your own research. And then once you're kicked out of that, you're into sort of more the into more the soft money. So one thing that yes, sort of people interested in this career needs to realize is that a lot of your time is sort of devoted to getting money through grants, like maybe even half of your time might be that, and but you also can sort of be kept afloat sort of if you have a teaching gig as well. So yeah, certainly you won't be able, about sort of 5% of your time is sort of eureka moments, and but yeah, I mean, you do yes, I think I'd say maybe like 40% of my time also is sort of doing hard science. A lot of time is proposals and sort of also reviewing proposals as well. That's sort of the cycle that we go through, and so you need qualified scientists to review others' proposals. I think one thing that's maybe helped a bit, one thing I realized is probably valuable for people is, well, it certainly helps to have sort of specialists who sort of focus on a narrow sort of narrow topic, to make yourself as valuable to the community and to sort of be able to sort of like apply to as many sort of proposals as possible, and sort of be as attractive to as many other investigators and collaborators as possible, is to sort of try and sort of try and sort of be involved in something that's sort of as diverse as possible. For instance, one thing Leslie mentioned is that I do a lot of landform evolution modeling, and the model we use is very flexible. You can apply it to a lot of different places in the solar system, a lot of different environments. I tend to do a lot of outer planet stuff, but I could also, without it was originally made for Mars, and with not much sort of goading, I could sort of be used, it could use to turn attention to sort of more inner solar system environments. So yes, it's it's inevitably you'll specialize in some field or other, like I do landforms and sort of topography, others focus on things like meteorites and things. It is worth keeping sort of, not being too sort of shoehorned into such a small space, and sort of, make sure that, yes, you can be as appealing to as many potential collaborators as possible. Yeah, because, that's, I think, probably the best way, certainly sort of help financially to be able to be as valuable as possible, and therefore sort of be open to as many possible avenues for funding. Yeah, and not just within, not just proposals, but also sort of outside the sort of NASA as well. A lot of the money we get is from NASA proposals, but also maybe sort of contracting with sort of private companies as well. I don't really have much experience of private industry myself, but yes, of course, with the growing interest in space companies, and at some point it's not going to be just engineers and rocket scientists they're employing. There'll also be actual sort of geologists as well. Once we actually sort of start getting to these places, there will be far more far more demand, as opposed to
like
just us in our ivory towers at the moment.
It seems like a good note to end on. Advice to kids to keep money and funding and employability in mind, and study broadly, right?
I think so. Yes. Yeah.
Absolutely.
Well, Leslie, I know we're over our time. Should we go ahead and wrap it up?
Yes, Oliver, thank you so much for answering all of our questions and for sharing all about Pluto. I think we've all learned a ton today, and we really appreciate you taking your time to be with us. I'll turn it back to Mark to kind of close us out.
Yeah, and I'll be very quick today because I know we're over time, but thank you to Oliver for joining us and for the presentation. It was a really great different flavor for this series, just to give people a sense of what that those 5% of eureka moments, if you're working as a scientist on a mission, career making mission like that, it's pretty great. And thank you, Leslie, as always, for taking the time to come and host these. And thank you, Rebecca and Tasha and Laquita. She had to take off, but everybody that asked questions today, just fantastic to have people here live, because those are totally different questions than Leslie and I would have asked, and we're happy to have you guys here. So thank you, everyone. I'm going to go ahead and end the recording as usual. Happy to stick around for a couple minutes, but then I got to go check on the kids.